And next example, which is the last example in this chapter, and we are going to use binary outcome variables. And RESP.SAV contains data from RCT. Patients in each of two centers are randomly assigned to groups receiving active treatment or a placebo. During a treatment, respiratory status, quoted here 0 as poor and 1 as good, was determined for each of 4 visits. The variables center, treatment, sex, and baseline are binary categorical variables. And the variable age is a continuous variable. We want to assess the effect of the active treatment on the respiratory status. So if we go back to the data set, and so this person and this person, this is the baseline measurement. So this person has a poor respiratory status at the baseline. And visit 1, and this person still have a poor outcome. Poor. Okay. And then ID number 4 person, so this person, and this person has a good respiratory status at the baseline. And visit 1, this person had good, and the second visit good, and third visit good, the fourth visit, and outcome become poor status on the respiratory function. Okay, so this is the data we have. So at the baseline, and you have a similar percent of a patient and who has good respiratory status between two groups. Placebo is blue and green is active treatment. And so we can guess randomization worked. In the first visit, and you have a higher percent of patients with a good respiratory status with active treatment, and less number of people with a good status with placebo, and that gives odds ratio of 2.25. So also having a good outcome is 2.25 times larger with active treatment at the visit 1. And visit 2, odds ratio became 3.778, so the difference became greater. And visit 3, odds ratio 3.1, and visit 4, and odds ratio of 2.01. Okay, and let me show you how to compute odds ratio at each visit. Okay. And we are going to split the data by each visit. By splitting data, and we are getting rid of repeated nature from the data, right? Because a visit 1 contains only data from a first visit, so you don't have to worry about using repeated measures. So what we do is we split the file based on visit number and then run the logistic regression, and that will compute this odds ratio. And if you want to put the p-value in, yes, you can get the p-value from the logistic regression. So first you split the data by visit, and then perform binary logistic regression, not the GEE in this case, because within each splitted data and there is no repeat. And so you put the follow-up respiratory function outcome as a dependent and treatment. So covariate, and let's specify categorical box, and we want the first category to be a reference. And okay, right? So this is how I computed visit-specific odds ratio of a treatment on improvement of respiratory function. And so what we want to do next is, instead of computing each different odds ratio, and we want to pull these 4 odds ratio, because when you show 4 different odds ratios and then multiple comparison could become an issue, and also readers of your paper might get confused with having too many different effects. Okay? So when you eyeball this, and if you judge there is not much difference and you are okay to pull, and then we can unsplit the data, and then let's pull these odds ratio. How can we pull? That means we adjust visit, and then get the visit adjusted odds ratio of a treatment. So to do that, and now we are utilizing entire data set, so there is a repeat, and we can no longer use binary logistic regression. So we go to GEE now, and put the ID under subject and visit under within subject variables, and here, and we an impact in GEE when you have no missing data, and every single patients have the same number of observation. In this case, if everybody have a measurements on all for visit, and then choice of correlation structure doesn't really matter. In GEE actually do have iteration in computation. So even when you guess initial correlation matrix as an independent, by iterating this process, and GEE will converge to a right correlation structure. This is the difference between GEE and a mixed effect model. Mixed effect model uses a closed formula. So if you guess wrong correlation structure, and that will impact on the p-value. And although in GEE, as long as you have a balanced data, that means everyone has the same number of observations. If everybody have 4 visit data, and then you have a balanced and no missing data. And in this case, whichever correlation structure you use, the model will converge to a right correlation structure. But when you have missing or unbalanced number of observations between patients, and then GEE can bias the result. Okay, so in that case, it's better to start with the correct correlation structure. And so let's go back. Okay, and here, right, outcome is a binary, so you click on binary logistic, and response is a response follow-up, and here this box got highlighted, so you click on reference category, and it's important to make this to the first choice, and otherwise your odds ratio would be reversed. So click on first and continue, and predictor, and now, and we put the visit under factors. So we first consider visit as a categorical variable, and the treatment also under factor. And then here we need to specify descending order. And in this case, the treatment 0 would be reference category, and so as visit 1 being a reference category. And then go to model. Under the model, you put the treatment and visit, and you skip estimation, go to statistics, and let's click on include exponential parameter estimate. So this way, you don't have to use the calculator to exponentiate beta coefficient to convert to odds ratio. Okay, and then I think we're ready to click OK. And this odds ratio 2.688 is a pooled odds ratio of effective treatment and over for visit. And this is pooled odds ratio. So if you get rid of a visit from the model, and this would be a predicted value based on this model, and as you see here, you see a flat. So there's really no difference made by visit. And then this odds ratio and the model estimate is 2.679. Okay. And on the other hand, and if you put the visit in the model, a model actually do recognize differential effect by each visit, like second visit, and you have a smaller number of good respiratory function for both active and placebo groups. And then visit 1 and visit 3, and you have more patients with a good respiratory function. Okay. And although odds ratios are estimated being the same, so this odds ratio is 2.688. Okay, so you see similar difference here. And now next, So let's see what happens if you include interaction method here.